All right, so for part 2, we're going to be starting with graphs and rates of change. So question 14 here asks us to find each of the following for the graph of f shown. So f of b, for that we're going to evaluate where b is, and we notice that's right here at this point r, so we know the answer to this is r. Next, we're asked to solve f of x equals r. We notice there's 2 points here which give us that value. Therefore, for this one, x could be b or d. Next question asks us to find f of x equals 0. When looking at this graph, we notice that both these ends are going up in the positive direction, and therefore our graph never actually crosses 0. So this value does not exist. Next, we're asked to name the intervals on which f is increasing. So here we can see from c on, our values are increasing, and for our interval, it will be c to infinity. The average rate of change on the interval c to d, and then we're asked, is it positive, negative, or 0? So our points c to d are here, and we can see that's increasing. Therefore, our average rate of change needs to be positive. Part F asks, is fd minus fb divided by d minus b positive, negative, or 0? This formula here is actually just the average rate of change. Therefore, what we're really asking is the average rate of change between b and d positive or negative or 0. Well, these values are at the same point. Therefore, our average rate of change will actually be 0. Now we're asked to name the intervals on which the rates of change are negative. Well, it's going to be anywhere that our graph is decreasing. So this should be negative infinity to c. Last, we're asked to name the intervals on which the rates of change are increasing. So for this one, we need to think about the concavity of our function. Well, this entire portion here, this entire function will be concave up. Therefore, the intervals on which our average rates of change are increasing is going to be negative infinity to infinity. Question 15 asks us, if g is a decreasing function, then which is the largest? Since g is decreasing, then the x value that is farthest to the left must have the largest y value. Therefore, our answer here is going to be g of negative 8. 16 asks, if h is an increasing function that is concave down on the interval 0 to 2, where is the rate of change largest? Since the graph is concave down on the interval 0 to 2, and rates of change for concave down intervals decrease from left to right, the rate of change must be largest at the left endpoint of the interval. Therefore, our answer here would be A. 17. Suppose a function f has average rates of change as shown in the table. So from 2 to 2.1, we have negative 1.5, 2.1 to 2.2, negative 0.38, and so on. Part A asks, would you expect the graph of f to be increasing, decreasing, or neither on the interval 2 to 2.6? So 2 to 2.6 encases this entire interval here. So from here we can see our average rates of change are all negative. Therefore, we'd expect the graph to be decreasing. Part B asks, would you expect the graph of f to be concave up, concave down, or neither on the interval 2 to 2.6? Well, we can see that our average rates of change are negative, but they're actually increasing. Therefore, we'd expect our function to be concave up. For question 18, we're asked to assume the graph has domain negative infinity to 6 and all relevant features are shown. So using interval notation, estimate the entire x intervals where the graph is increasing and concave down. So that one is going to be from 3 to 4. rest where it's increasing and concave up. So it's going to be back here from 2 to 3. Decreasing and concave up. So it would be from negative infinity to 2. And decreasing and concave down. This will be from 4 to 6. Now we're asked to find the local and absolute maximum and or local minimum. Write D and E if it does not exist. So our local maximum, we can see here at 4, 7. So our local maximum is actually the y value of 7. Our local minimum is here at 2, 3. So again, our local minimum is what that y value is, which is 3. For the absolute maximum, we can see on the left, this function goes to infinity. So for that, we say the maximum does not exist. And for the absolute minimum, we can see the function ends here at 6. So our absolute minimum should be negative 13. Now for the approximate point of inflection, it's going to be where our concavity changes, which is right here. So that point will be 3, 5. Question 19 says to consider a function f that is the domain of all real numbers. Sketch a possible graph of a function g with the following properties. The rate of change of f is negative on infinity to 3 and on 5 to infinity, negative infinity to 3. The rate of change of f is positive on 3 to 5, and the graph of g is concave up on negative infinity to 4 and 4 to negative infinity. So our major points we need to watch out for are 3, 4, and 5. Because 3 is where we're going to be changing from negative to positive. 5 is where we'll be changing from positive to negative. And 4 is where we'll be changing concavity. So an example of a function we could write could look something like this. So now using that graph, we'll answer parts B and C. So at what x values does a local maximum or a local minimum occur? And we can see here, this should be at 3 and 5. Where 3 would be our min, and 5 would be our local max. What is the x value of the inflection point for this graph? So this is going to be what our concavity changes, and that happens here at 4. So this is at x equals 4. For question 20, we're asked true or false, if a function f is decreasing and its graph is concave up, then the rates of change of f are negative and they are getting larger when moving from left to right along the graph. So this is true. And the reason is, if the function is decreasing, then that means that our average rates of change will be negative. However, if we have concave up, this means that our rates of change are increasing. Therefore, we'd expect them to be getting larger. All right, we're going to start out with question 21. So before getting started, I'm going to point out this idea here. The limit as x approaches infinity of 1 over x is equal to 0. So the idea here is if we look at term by term, if 1 over 1, we know that's 1. We have 1 over 10, we know that's 0.1. 1 over 100, we know that's 0.01. And you can see these terms are all approaching 0. So So starting off with part A, we're told that y equals 1,000 over x plus 1. So when we're taking the limit as x approaches infinity of y, one thing we can do is we can multiply the numerator and denominator by 1 over x, which is our leading power. this will yield us with 1,000 over x over x over x plus 1 over x. So when we take the limit as x approaches infinity of this, for x over x plus 1 over x, we know these terms will become 0, 1, and 0, which then gives us the answer of 0. Part B, we're given the function y equals 5 minus 1 over x. So when we take this limit as x approaches infinity, we can view it term by term. 5 minus the limit as x approaches infinity, 1 over x. So I give us 5 minus 0, meaning our answer is just 5. Part C, y equals x minus 4 over x squared plus 1. So we use the same idea as we did at part A, but in this case, we're going to want to multiply it by 1 over x squared. And the reason being that x squared is our highest power in our denominator. This would give us x over x squared minus 4 over x squared over x squared over x squared plus 1 over x squared. This would give us 1 over x minus 4 over x squared, 1 plus 1 over x squared. So when we look at the limit as x approaches infinity of this, our terms will become 0 minus x squared just means it's going to go to 0 even faster, over 1 plus 0, meaning our answer is 0. Moving on to question 22, we're told that y equals x minus a over x minus b, where a and b are real numbers. So we can use the same idea here. We multiply the denominator and the numerator by 1 over x. This would give us 1 minus a over x over 1 minus b over x. And now, since a and b are real numbers, these terms will be approaching 0. So that means when we take our limit as x approaches infinity, this function, we'll get 1 minus 0 over 1 minus 0, and that just equals 1. Question 23 states that salt water is flowing into a large tank, and the concentration C of salt in the tank is given by C equals F of T, which equals 1.2 T divided by 100 plus 6T in units of pounds per gallon, where T is the time in minutes after the salt water started flowing into the tank. So we're asked, what is the concentration of salt water 10 minutes after salt started flowing? In other words, we're asked, what is F of 10? So for this, we'll just plug in 10 everywhere that we have T. This will give us 12 over 160. And this is equal to 0.075 pounds per gallon. Part B asks what happens to the salt concentration as T approaches infinity. So in other words, what's the limit as T approaches infinity of our function? That would be the limit as T approaches infinity of 1.2 T over 100 plus 6T. So to evaluate this, we need to multiply our numerator and denominator by 1 over t. This would give us 1.2 over 100 over t plus 6. And if we take the limit as t approaches infinity of this, it will leave us with 1.2 over 6. And that's equal to 0.2 pounds per gallon. For question 24, we're asked if f of x equals 6 minus 5x, then as x approaches infinity, what will f of x approach? So if you think about our graph will have a y-intercept of 6 and a slope of negative 5. So from here we can see this is approaching negative infinity. Therefore our answer will be negative infinity. Then we're asked if the limit as x approaches infinity of g of x equals 3, and if h of x equals 7 g of x minus 2, what is the limit as x approaches infinity of h of x? Well, for that one we can evaluate term by term, which means we can view it this way. Infinity 7 times the limit x approaches infinity of g of x minus the limit here as x approaches infinity of 2. Well, this will give us 7. We're told that this equals 3 minus 2. It's 21 minus 2, which equals 19. Question 25. A rock tossed in a pond creates a circular ripple with area A equals f of r square meters when it had a radius r meters. The radius is r equals h of t meters at time t seconds after the rock hits the water. What is the meaning of f of h of t? Well, here we know this is ultimately equal to a, and our input here is time. So the input is time, and the output is area. So this function gives the area at time t seconds.